This video is on differentiating and how to use that to find the gradient at different points of a curve. Now, we are just going to go straight into how to do this. Okay, so if we had y is equal to a number k times x to the power of n, then this differentiates to, so we denote that dy over dx to, so this n, this power here, you multiply at the front, and then the k is still there, and then the x is there, but the power goes down by 1. Okay, now this is a different way to denote it as well. Okay, so we have fx in place of y here, and otherwise it's the same, and in place of dy over dx we have f dash x. Okay, and then this is the same as that. Okay, so there are two ways of writing it. Now let's see how this works. So we have differentiate y equals x squared. Now my k here would be 1. Okay, so that won't change anything. Now my n here is 2, so I can see that the n, when I differentiate, if I was to write dy over dx, so dy over dx will be, okay, so the n comes to the front, so this 2 is going to come to the front, so I'm going to have 2 times, now k is 1, so I don't need to write that one, and then I've got x, and then I need to do n minus 1 here. So 2, my n was 2, so 2 minus 1. So 2 minus 1. So this is going to be equal to 2x. And 2 minus 1 is 1, so I can just write it as 2x. So if I differentiate y equals x squared, dy over dx is equal to 2x. Okay. Now also, this doesn't show it, but if I was to have plus k times, plus a different number, times x to the power of a different number, you would just do the same process as you're doing here. Okay, and you'll see that in other examples. So we have the next one. This time for this part, so we're going to do each part separately, but this one doesn't have an x, so I'm just going to put that in for now. So I'm going to say y is equal to x to the power of 3 plus 3. Now what can I put? I can put x to the power of 0, because anything to the power of 0 is just 1, and then 3 times 1 is still 3, so I haven't changed anything there. So I'll do this one and this one separately. So this one, my n is 3, so when I differentiate it, so if I wanted to write dy over dx, just move that, is equal to, so n is 3, so and k is 1, so 3 is going to come to the front, so I'm going to have 3 times, now k is 1, so 3 times 1 times x to the power of 1 minus this power, or this power minus 1, sorry. So 3 take away 1, which is 2. So it's going to be 2 there. And I'm going to have plus. Now this 0 is going to come to the front, and I'm going to multiply it. So it'll be 0 times something, and that's just going to be 0. So this one is just equal to 3x squared. Now notice how whenever I have a constant here, that just disappears when I differentiate it. Okay, so I'm working with this one, and the constant here, it disappears. It's not there anymore, because that 0 would come to the front and make it 0. Now here again, we can see that this is just going to become 0, but these two parts, okay, let's see how these will work. So when I differentiate it, I'm going to write dy over dx, dy over dx is equal to, okay, so n is 3, k is 2, so the 3 is going to come to the front here. 3 times 2 I'm going to have, so I'm going to have 3 times 2 times x, and this power is going to go down by 1, so it's going to become 2. Okay, and then I have this here, so here my k is actually minus 1, okay, and then n is 2, so the 2 is going to come down, so 2 times minus 1 is minus 2, so minus 2. And if I take away 1 from this power, it's just going to be x to the power of 1, which is just x. Okay, and if I simplify that, I will have 3 times 2 is 6. So I'm going to get 6x squared minus 2x. Okay, now so far we haven't really used it for anything. We're just looking at how to go from the equation with y and how to differentiate that to make it dy over dx is equal to something. Okay, but we'll see how we use it afterwards. Now this one's given as fx, so I'm going to write, when I'm differentiating it, I'm going to write f dash x. Okay, and then again it's just the same process. Okay, the 4 is the n, so that comes to the front, so I'm going to have 4 times 2x to the power of 3 because the power needs to go down by 1. And the next one is just going to be minus 3x squared. And the next one is going to be, the 2 is going to come down, so 2 times 5x. Okay, and then the last one, this is just going to become 0 here. Okay, so if I simplify that, I'm going to get 8x cubed, and then I have minus 3x squared, and I have plus, or 2 times 5 is 10, so I have 10x here. Okay, so this here differentiates to 8x cubed minus 3x squared plus 10x. Now, you don't have to write this middle step. You can just think, okay, 4 times 2 is 8. And if I minus 1 from this power, it's going to be x to the power of 3. And then the 3 comes down here, and minus 1 from the power. And here, 2 times 5 is 10. Minus 1 from the power, you're just going to get x there. Okay, so this is how you differentiate. Now, here is a use that we can have for differentiation. So we have a description of what we have here as a function and here as a graph. So I have a golf ball is struck such that the highest point it reaches above the ground is 50 meters and it lands 40 meters away. Now we're going to let x represent the distance the ball has traveled forwards and fx be the height of the ball above the ground. Okay, and this equation here represents this function that's described there. Okay, so fx, this is going to, this here is going to output the height of the ball above the ground when you put in for x how far the ball has traveled forwards. Okay, so this is what the graph will look like. So the ball is traveling forwards this way, and this is the height of the ball. Okay, and it goes down. Okay, now what can we do in terms of differentiation and this graph and what it means in our example? Okay, so let's differentiate this first and see how that's going to work. So when I differentiate it, I'm going to write f dash x is equal to, okay, so now I need to look at this. So this 2 is the n and my k is minus 1/8. Okay, so 2 times minus 1/8. So I'm going to have 2 times minus 1/8. And if I take away 1 from this power, I'm just going to have x. So it's going to be x. And the next one, this power here is x to the power of 1. So the 1 is going to come down. 1 times 5 is just 5. And then if I minus 1 from the power, I'm just going to show that actually. So I'm going to have plus 5 and then x to the power of 1 take away 1. Okay. So this is now going to be, let's write that again. So 1 take away 1. Okay, so this, now if I simplify this, so 2 times minus 1/8 is going to be minus 1/4. So let's write that. So this is going to be minus 1/4 x. Okay, and here 1 minus 1 is 0. X to the power of 0 is just 1. So I'm just going to get plus 5 here because that's going to be 5 times 1. Okay, because this is going to be x to the power of 0. X to the power of 0 is 1, so 5 times 1 is just 5. Okay, so when I differentiate this, this is the result that I get. Okay, so let's just write that here as well, f dash x. Okay, so this is my result. Now, so this is, when I'm differentiating, this is supposed to give me the gradient. So this actually gives me the gradient when I put in a value for x. Okay, so let's say, for example, when the ball has traveled 4 meters away, what's the rate of change in terms of how high it's going with respect to how far forward it's traveled? Okay, so we need to substitute 4 into here, and this is going to give us the gradient at this point. Okay, so let's mark that point. So 4 is, we're looking for the gradient at this point. So if I do f dash 4, this is going to equal to minus 1/4 times 4, add 5. Okay, so minus 1/4 times 4 is just minus 1, and then add 5. Okay, so I'm going to have, that's equal to minus 1, add 5. So that's equal to 4. So at this point here, the ball is traveling 4 meters up. If we think about if we're thinking about 1 meter forward, it's traveling 4 meters up. That's the rate of change at that point. And I can see that here it's actually quite steep, but here it gets a little bit flatter. Okay, so I'm expecting it to travel fewer meters up, and as I'm going forward 1 meter. So if I try, let's say 16. Okay, so let's try 16 now. So when x is equal to 16, let's find the gradient here. It should be less. Okay, so here we have the gradient of 4. Let's see what we get here, what we get there. So I'm going to have f dash 16. That's going to be equal to, okay, minus a quarter times 16 and add 5. Okay, now let's see what that gives. So 16 times minus a quarter, that's going to be minus 4. So minus 4 add 5. So I'm going to have minus 4 add 5. That's equal to 1. So the gradient here is 1. Okay, so it's not really moving up that much for how far forward it's going. Okay, and here it was moving up quite a lot for a little bit forward. Here it's not moving up so much anymore. Okay, and then here we can see it gets flat and then it starts to go down. Okay, so let's try some values here, see if we get a negative gradient there. So let's try the value 24. Okay, so let's try 24. So I'll mark it on the graph. So we're looking for the gradient here now. So I have f dash 24. Okay, so what's that going to be equal to? So minus a quarter times 24 add 5. Okay, so 24 times minus a quarter, this is going to be minus 6 add 5. So let's do that. So that's going to be equal to minus 6 add 5, and that's going to be equal to minus 1. So here the gradient is negative and it's slowly gathering speed and it gets really quick when we come down here. So we're expecting the gradient to be negative, but a low negative. But let's see what the gradient is here. So has it gathered some speed, and is it coming down much quicker here than it was there? So let's find the gradient at x is 36. So when the ball is 36 meters away from the person that hit it. So 36 is here. So we're looking for the gradient here now. So let's find the gradient there. So if I have f dash 36, I'm going to get minus a quarter times 36 add 5. Okay, so 36 times minus a quarter, that's going to be minus 9. So that's going to be equal to minus 9 add 5, and that's going to be equal to minus 4. Okay, so the gradient at this point is minus 4. So if I compare it to the gradient here, or the gradient here is negative, so it's coming down, but it's coming down very slowly because it's minus 1. But as it's coming down more and more, it's gathering more speed, and at this point the gradient is minus 4. It's coming down really fast for how far forward it's going. Okay, so the gradient is minus 4 as we expected. Okay, so this is how you can use, so after you differentiate a function like this, you can substitute values for x to find the gradient at different points of the curve. Okay, this function, okay, so if I substitute a value for x here, I will just get how high the ball is. Okay, because that's how we define the function. So if I say, for example, I substitute 20 here, so 20 into there, 20 into there, I should get 50 because the highest point is 50, and you can check that to see if we get 50. Okay, so this function describes how high the ball is when we input the value of how far forward the ball has traveled. Okay, and this gradient function, this tells us what the rate of change is of how fast it's going up compared to how far forward we're going. Okay, so with rate of change for the gradient here. Okay, now here are some questions for you to try. So it's just 3 equations here, or 3 functions here that you're going to differentiate, and then I want you to find the rate of change of y with respect to x when x is equal to 3 for the functions above, so these functions here. Okay, so do these questions and then bring that to the lesson.